Hello, and thank you for the opportunity to present to you some of the work that we are doing in developing robotics for retinal regenerative therapy delivery, and in the process of doing that, give the broader explanation of the state of the art in robotics across the international spectrum as well in the field of ophthalmic surgery. I'm Christos Bergeles from the School of Biomedical Engineering and Imaging Sciences of King's College London. The problem that ourselves and other groups internationally are trying to address is age-related macular degeneration. Age-related macular degeneration is the progressive loss of central vision, similar to this, which results in the inability of somebody to navigate in a text, to be able to read, to be able to look at spaces, because the central vision is lost. So while the peripheral vision is retained, and so there is some spatial awareness, age-related macular degeneration implies that we are losing the highest part of the most important part of our sight, which is that central part which is located near the macula. In the UK alone, there are around 700,000 people that suffer from age-related macular degeneration. In the world, there are around 200 million people that suffer from age-related macular degeneration, and its two manifestations, dry AMD and wet AMD. And dry AMD accounts for around 90% of the cases. Wet AMD can be managed with the administration of drugs that inhibit vascularization, which is the form that this disease manifests, but dry AMD does not have a cure yet. The total cost of foreign economy of the size of the UK, just for the AMD, due to sight loss and due to requiring care, requiring injections, is almost 2 billion. So it's an enormous amount just for this disease. And even though 2 million people suffer from sight loss across the UK, so that AMD accounts for less than 50%, it accounts for almost 70% of the total costs, because it is a disease that cannot be managed, that progressively leads to complete blindness in otherwise healthy individuals that are age 60, 70 and above. So what do we want to do? We want to understand how AMD develops and work together with clinical and biology teams in order to deliver these therapies that would combat dry and ultimately also wet and AMD and other diseases of similar nature as well. So if we take a picture of our eye, this is how our normal vision would look like. Healthy, that black spot in the middle is the point of highest vision. This is how dry AMD would look like. And you can see there all these bright spots that develop in the middle. And these dry spots, if you look under the surface, are happening because there is what we call a retinal pigment epithelium degradation. So when in dry AMD, what happens is that a specific layer in the eye, the retinal pigment epithelium, dies, so the cells become apoptotic. And this retinal layer is the one that is responsible for supplying nutrients to every layer above it. So in other words, because there are no nutrients being provided to the photoreceptors, they are the ones that become apoptotic, and then vision is lost. So what we would like to do is to be able to go to this specific retinal pigment epithelium layer, and ultimately in other layers, should we wish to inject therapies, and redeliver the cells that have been lost. And this is what we want to do within the context of vitreoretinal surgery. Vitreoretinal surgery is a surgery that takes place in the back part of the eye, inside the vitreous humor above the retina. It is an extremely challenging procedure that requires micromanipulation, as little hand tremor as possible, and usually the forces that are applied are on the order of human perception and even below human perception. So they are very hard to perceive. So everything happens due to vision. And ultimately what the surgeon wants to do is not to touch the retina, because when there is a touch event, usually there is damage. So we would like to not only be able to carry out the vitreoretinal surgery, but also do these interventions that are otherwise impossible to be done by the surgeon. And this means the delivery of regenerative therapies. So this is how, from the biomicroscopy images, vitreoretinal surgery looks like. You have very tiny instruments that navigate the interior of the eye. They need to dissect elements, they need to pick up elements, they need to remove membranes. But ultimately, what we would like to do is to go within the retina in order to carry out these interventions. And that's where things become even more interesting, because this is the structure of the eye. What you see there in the red box is the macula, and this is where we are interested in delivering these therapies. Now, the eye is like an onion layer, so it is like an onion, so it has multiple layers, and each one of these layers has a specific function. So one layer would be the photoreceptors, the other layer would be the ganglion cells, the other layer would be the retinal pigment epithelium, and at the back of the eye all the way is the retinal pigment epithelium, which we discussed before, which is a monolayer responsible for supplying nutrients to the photoreceptor above and beyond. So when the retinal pigment epithelium degrades, the photoreceptors die. We can reach the retinal pigment epithelium now with some specifically crafted instruments that clinicians have developed, like our collaborator Lyndon Da Cruz and his biology collaborator Pete Coffey at UCL. Because between the RPE and whatever is after it, there is a natural cleavage plane, and then you can access it and it acts like a stop. But if you want to go anywhere in between, any other of these layers, this is not possible by hand, and this is where robotic assistance is paramount. And to illustrate this better, imagine that we have the human hair, and this is an image of the human hair under a scanning electron microscope, and we cut the human hair, let's say 10 times. What we need to do is to go between those cuts and deliver sustained dejections there. And over a prolonged period of time, even up to several minutes, we want to be slowly dripping therapeutics very stably, very precisely, in order for these therapies to be uptaken by the cells rather than flooding the entire system. And that's what we want to do. And to illustrate it even better, if we assume that the eye is 1 centimeter, so 10 millimeters, which means 10,000 micrometers, each one of those layers is around 10 micrometers. So we have 1,000 to 1 ratio of how far we are versus the precision we need to target. So it's as if we have a 1 kilometer stick and trying to flick, a 1 meter switch. And so this gives a sense of the precision that these surgeons would need to have. Of course, this is not possible by the human hand, and therefore the precision that our robotic systems should have. And in order to do that, we're going to use images like this one. They are called optical coherence tomography images, and they nicely delineate the layers of the human eye, which you can see there with a variety of colors. Now, of course, this is then going to guide the injections. So at these variety of layers, we would go with our robot and deliver the injections as we discussed before. But the reality of these diseased eyes is much different. You can have subretinal fluids. You have layers that are vanishing and then reappearing. You have layers that are completely gone. You might have complete absence of that cleavage plane that I was discussing before. And that's when robots become even more important in these pathological cases, in which case they need under-image guidance to be able to go to the layers of interest and then deliver the drugs and the therapies there. This is what Professor Da Cruz and Pete Coffey have been making over the last 20 years. It is a full pipeline of how to create stem cells in order to go in the human eye and deliver those cells that have been missing. So what you see on the top is a healthy retina. R signifies the retinal pigment epithelium and P the photoreceptors. And this monolayer that you see just above where it says healthy retina, this is the monolayer of the retinal pigment epithelium. And what you can see in the diseased retina is that this monolayer is absent. and then the photoreceptors are gone. And this is how it manifests from this 2D and fast image that I showed you in the beginning of this lecture. So what we want to do is to be able to go, at least as a first step, and redeliver this retinal pigment epithelium using cells that have been harvested and created in the laboratory environment. And this is indeed what their biggest success has been so far, in my eyes, of the engineering eyes as well, at least. They are able to take skin cells, revert them in the lab to their primordial state of stem cells, and then regrow retinal layers from there. And then these retinal layers will be recovered and inserted back into the eye in a sheet, arranged on a sheet. And they have shown with the first clinical trials that they have done that sight can be regained for the patients that underwent surgery and reimplantation of stem cells. So this is a tremendous achievement. But then now the next question is, well, if we want to go and do this more precisely, more repeatably, more availably, and even go and change other types of layers, what can we do and how will robots come in play? So this is the research that we are aiming to do in my lab and other labs as well. We are trying to develop robotic systems that either in a telemanipulated or a co-manipulated fashion augment the capabilities of human surgeons in order to deliver therapies precisely under image guidance. There is a variety of systems that have been developed, and they are fascinating pieces of technology, and they can be classified in 4 different categories. We have micro-robotic systems, handheld systems, co-manipulated systems, and teleoperated systems, and I will just showcase a few of them in this talk to give the overview of the domain. A handheld system will be discussed first, and these are completely ungrounded systems that record human motion and human tremor, and then try to decouple tremor from motion and counteract it. Co-manipulation systems, such as the ones developed at Johns Hopkins in K11, aim to supplement the capabilities of the surgeon, either via impedance or via admittance control, and they are increasing the precision of the surgeon while not drastically changing the workflow. Finally, another category is the telemanipulated systems like the one from Precise, which has been commercialized, wherein there is no physical link between the robot and the surgeon, but rather the surgeon is moving the instrument and therefore moving the robot, moving a handle and then moving the robot. And finally, our approach as well, which is a co-manipulated system, and I will show you some of the results that we have done in the domain. Microrobots is kind of a niche in the sense that there is no tether between the end effector of the instrument and the actuation system because it uses electromagnetic fields in order to do the motions. So the first system we will discuss is called Micron, developed by Cameron Riviere's team at Carnegie Mellon University. And what you can see is that when Micron is off, these LEDs that are on the handle, they move, whereas when it's on, there is a decouple between what is on the shaft and what is more on the distal end. And through a very tiny parallel manipulator, parallel actuator, that is able to remove the motion, but also servo the tip in order, under image guidance, for example, to do very well spread out cauterization of the retina. And there is a visual servoing scheme that looks at where the vessels of the eye are and makes sure that the tip is reoriented according to the plan, so the plan adapts alongside the surgical view. This is the steady hand from Johns Hopkins University. And the concept of the steady hand is that there is a force torque sensor at the base of the handle. This records the forces of the operator, and if the forces are deemed admittable, then it passes them onto the robot, which scales them and creates a motion profile based on those forces. So this means that inadvertent motion can be filtered out. You can apply virtual fixtures, you can guide the operator, and generally you can increase the precision of surgery while retaining the posture that the surgeon is used to, for example, looking through the BioMicroscope. And this is an example of peeling a small sticky tape from the back of an eye. Similar concept is at K11 as well. The primary difference here is that this robot is counterbalanced. So it is fully, when it's not touched, it's stable. And it works based on impedance. So it will make the surgeon move slower. So it would hinder the surgeon's motion. But the principle is the same. The surgeon and the robot are moving the tool together. And this instrument has also been evaluated in a human trial and cadaveric studies, as far as I know, and showcases that you can, with such instrumentation, be able to target even the smallest of retinal vessels. The most well-known telemanipulation example is a system of Precise. Precise is taking kind of a mix of the two paradigms. What happens is that in order not to take away the surgeon from their natural position in the operating room, they put the handle somewhere that it seems close to the natural position when operating in the eye. So you are flipping the robot so that it comes into the eye, then the handle is moving the robot, but the surgeon is, they're close. They're not that detached from the surgery itself. They are able to have very high precision, and the system has been evaluated in human and also for subretinal injections, which is different than intraretinal injections, but still a very important milestone towards achieving the end goal. The work we are doing has three pillars. We are focusing extensively on the design of the robotic systems, on the modeling of the robotic systems, and how to couple image-based information in order to achieve prolonged therapy delivery. In order to most appropriately design our robots, we try to model everything that exists in the operating room. So we modeled the bed, the microscope, the space under the bed, where the legs of the clinician would go, because what we would want is ultimately very compact systems that do not obstruct workflow, but also take minimal space within the operating room in order to reduce the setup times. When it comes to modeling, we looked into the dynamic modeling of transmission systems, including friction, and specifically how we can work with start-stop operations. So one of the issues with these microsurgical robotic systems and microsurgery in general is that you stop, you start, you move from one direction to the other. The start and stop cases are the ones that are the most challenging to model because friction transitions between the domains of moving and not moving. So we have developed very fast models, very fast dynamic models of the transmission systems, and we are now using these models in order to assess what is the smallest actuators that can do the job and make sure that we have the most compact systems rather than over-designing our system. We are also bringing these robots that we design within the virtual operating theater, where we have developed, and you can find freely available online, VRViz, which is a ROS plugin, where you can import your CAD models and then have them visualized through HTC Vive and be able to move them with the joysticks of HTC Vive. So you could use the goodies of ROS to solve the kinematics and the nice visualizations. And what this is actually you can now go within this operating room, you can look under the bed, you can see where the robot is, and this makes it easier to understand how the technology will ultimately be deployed. We're also developing more integrated approach based on flexible robotic systems. For example, this is some of our latest results. We have a flexible robot based on concentric tube technology, which is now positioned on top of a medical-grade KUKA manipulator with pass-through electrical connections. The KUKA manipulator then brings the robot to what we call the homing position, which allows a disposable tool to be plugged in on the actuator system. Motion is transmitted from the actuator system to the disposable tool, which has hollow lumen in order to allow for therapy delivery to be carried out. That the KUKA is bringing is aligning the robot with a trocar point in the eye. This is now scripted, but we are working on doing it automatic. And the flexible tool is inserted based from the entry position to inside the eye. And this concentric tube robot is optimized to achieve maximum dexterity near the retina. In other words, we have created a design optimization framework that iterates over a variety of designs in order to achieve wrist-like dexterity. Now, this specific tube system is not that one, but that's what our next iteration would be. And we are able, in this case, in open loop and with a very skilled operator, I have to say, because control is not yet finalized, we are able to go at various locations in the vessels and pinpoint their middle. So in that sense, we are able to have the accuracy we want, but building the user interfaces around that accuracy is now what we are trying to do. And the final technology that I'm very fascinated about is what takes place at Brad Nelson's lab in ETH Zurich. And they are creating magnetic micro robots. And this is part of the work that I had the pleasure of working in when I was in his lab as a PhD student. These magnetic micro robots would be either the heads of catheters these days, this is the research that their lab is taking, or they would be fully untethered and drug loaded. And you would inject them inside the eye using a normal needle, and the external electromagnetic fields would create forces and gradients and field in order to move and reorient a magnetic device to the location of interest. And this is some of the early experiments we had done where the microrobot was moving inside the cadaver eye of a pig. It is very easy to have very proper control when there is a vitrectomy because everything is smooth and works nicely. So when a vitrectomy is carried out, these robots will move fantastically. It is a little bit more non-linear and challenging to move them when there is intact vitreous. But what we showcased is that when using cadaver human eyes of elderly patients, which are the ones that will be afflicted by AMD, you are still able to move the micro device, let's say to follow a vessel. And therefore, this implies that this technology, either as an untethered magnetic device or as a magnetic catheter tip, will be able to deliver the drugs to the locations of interest. Thank you very much for your attention, and I'm glad to have presented to you the overview of the robotics field for retinal regenerative therapy delivery, alongside a couple of our research contributions that we hope to materialize in fully working integrated systems and pursue technology commercialization.